Hello, this is the first lecture of Physics 221, the first technical lecture anyway, and it's going to be addressing issues around Ohm's law and the topics of voltage, current, and resistance. And it's really talking about simple circuits, keeping in mind that a circuit consists of a power supply like a battery that will supply a voltage, which is something we'll talk about. There'll typically be wires which connect the battery to something else. And then there's a circuit element, which in this case is a light bulb, but could be other things like resistors, or you could have many wires and several circuit elements. But we're going to start off with the most simple circuit, which is a battery, some wires, and a circuit element. As this slide illustrates, the battery you can think of as, it's kind of like a pump. It pushes these little charges known as electrons that you studied in chemistry. It pushes them and forces them to go through the circuit. And that creates, when those charges move, they create a current. It's electrical current, unlike a water current, which would be water moving. Electrical current refers to charges that are moving. And the pressure that the battery exerts to do this is the voltage. So I use a lot of analogies when I'm addressing current and voltage because you can't see them. You can measure them, and we'll be using devices to measure them, like the meter that comes in the kit that you purchased. That will allow us to measure these things, but they're not things you can actually see that clearly. So I'm often using metaphors and analogies so that you can visualize what I'm talking about. So the battery pushes these charges through, and when the charges encounter things that are difficult for them to cross, a light bulb is an example, it's harder for the charges to go through a light bulb or through something else called a resistor than it is for them to go through a wire. So resistors, light bulbs, they're all, in a sense, resistors. They resist the ability of the charge to pass through it. They make it harder. So an example of maybe a physical example of a resistor is, I think, trying to get water above to go uphill. You have to push it in order for it to go uphill. And that's what the battery does. It pushes the current and allows the water to go uphill. It's one way to think about it. It's kind of metaphorically what's going on here. Another way to think about it is maybe there's a cup, like this mug here. Let's say there were a hole in the mug. If it were really small, the mug itself is kind of like a resistor. If I put water in here, the water wants to stay in the mug. But if I put a hole in the mug, the water would flow out of the mug. The bigger the hole in the mug, the more the water would flow out, the easier it is to flow out. So the wall of the mug itself is kind of like a resistor. If there's a tiny little hole in it, it's like a big resistor. If there's no hole in it, it's like a very big resistor. If there's a large hole in it, then it's like a smaller resistor. So I'm hopeful that that's helpful to you as you start to visualize these phenomena that we'll be talking about in this class. And you'll often hear me say, rather than a voltage, I'll talk about a voltage difference, which means that it's kind of like a height difference. When I talk about heights in first semester physics class, I might say something is 10 meters high, but that implies that I'm measuring from some other height that's 0 meters high. The same thing is true about a voltage. If you have a battery, like a 9-volt battery or a AA battery or something like that, that means that one side of the battery is at a higher voltage than the other side of the battery. And the voltage difference is the difference between the top and the bottom, if you like. So this side here, this is a 1.5 volt AA battery. You could call the bottom 0, the top is 1.5 volts. So we're really looking at the difference between the top and the bottom when I say a voltage. So you'll hear me use the word voltage and voltage difference quite a bit this semester, but they mean the same thing. And as I mentioned earlier, the voltage is kind of like a force. It pushes the current through the wire and through whatever is in the circuit that the current is flowing through. And I already mentioned this. The voltage can actually be used to cause things to do work. If the voltage is pushing current through, that current can actually make things do work and make motors spin, make light bulbs light. And we'll be talking about that and seeing that in lab. So this is a question I'm going to ask you. In this case, would you say that the waterfall represents high voltage or low voltage? And I mentioned earlier that current is the motion of charge, and you can actually think about it as the amount of charge that passes a given point in a wire or in a circuit in a given time interval. So it's kind of like a velocity, kind of like what we talked about in physics 1 with objects that are moving. The velocity of that object is its change in position divided by its change in time. Well, for current, the amount of current is the change in the number of charges that are passing past a point in a given time interval. So that's one way you can think about what current is. It's the motion of charge. We'll talk more about charge later in the semester also. Again, it's kind of like the number of electrons moving through a circuit. Now in this picture here, this is a photo of the Mississippi River. What would you say compared to the waterfall? In this case, would you say that this is you're looking at a large voltage difference? Like you said, like comparing it to the waterfall in comparison, would you say that this one is a big voltage difference? And would you say this one is a big or a small current as compared to the waterfall? So again, it's kind of like an analogy, but let's try to take that analogy to the case of water and see how that might relate to the current. If this was a current, would it be a big current or a small current? If it's a voltage, would it be a large voltage or a small voltage? How about in this case here? Same waterfall as in the previous photo. In this case, would you say compare the photo on the right to the photo on the left? Which one has the larger voltage would be one question. Which one has the larger current would be the other question. Think about that and answer the question that hopefully you'll see popping up in front of you on the video. Some things that you'll notice about current sometimes, hopefully you won't in lab. I've tried to design the lab so that this won't be the case, but if you have a lot of current flowing through wire, the wires can get kind of warm. You may notice sometimes electrical circuits can get warm, computers get warm, that's why they have fans in them. It's because of the currents that are flowing through the wires in the computer. Similarly, in a light bulb, traditional light bulb, like not a light emitting diode, but in light bulbs that they don't sell as much anymore, in the original light bulbs invented by Thomas Edison, they worked by the little filament in the light getting so hot that it would glow. But all the air was pumped out of the little bulb so that the filament wouldn't burn. The idea was it would glow but not burn. So they would get really hot. That's because of the current that was running through it. But it would create the effect that was wanted, which was light. It would also create a lot of heat. That's why light bulbs can also get very hot. We'll also see examples later in the semester that electrical currents can actually cause compass needles to change direction, and that'll be interesting. We'll talk about it later. And the other thing that's interesting is current will only flow in things that are good conductors, like wires, metals, on the periodic table that you probably remember from chemistry. The metals, copper, zinc, silver, gold, iron, those will all conduct electricity. Some of the metals conduct it even better than others, but they're all very good conductors. Electrons can flow easily through them because of the constituency of the outer valence shells of the of the atoms within the metal. That allows free flow of electrons. It allows currents to flow. Insulators like rubber or even cardboard, paper, those do not allow electrons to flow very easily. So those act as insulators, so when you touch a wire that's insulated, you won't get current flowing from the wire to you. The wire may feel warm, but it won't have current flowing out. That's why your plugs are coated with plastic or rubbery substance, because that acts as an insulator, because you do not want those charges, those currents, flowing through you for reasons that we'll talk about soon. It's a safety issue. And we'll be using the digital multimeter, and I'm going to spend time in the lab talking about that next week. So you'll get the opportunity to explore the digital multimeter by working with one that hopefully you've purchased and you'll own. It's a very useful device, but it will allow us to measure things like volts, amps, which is the unit for current, and ohms, which is the unit for resistance. I'm going to stop this video now, give you a break. You're welcome to watch it as many times as you want. And then the next video, which you're probably just really looking forward to, I hope, is going to address the topic of what it means by having things in parallel, having things in series, and using Ohm's law, which is the topic on the first homework and something you'll be using for a lot of the semester. So I'll see you in a moment.